I want to talk about the concept of increasing and decreasing functions. We're going to begin with the definition of what it means for a function to be increasing on an interval. So function f is said to be increasing on interval I. So an interval of x values if for all x values, let me say for all pairs of x values, x1 and x2 in I, where x1 is on the left and x2 is on the right. I don't mean of the left and the right of the interval. I mean, if you were to compare them, the two points x1 and x2, x2 is farther to the right than x1 is. Then f of x1, let me say f of x2 is at least as big as f of x1. So in other words, a function is increasing on an interval. So let's say my interval goes from here to here. If for any two x values, x1 and x2, for any two, for all pairs, I'm going to put that underlined, so we don't think that x1 and x2 have to be the endpoints of the interval. The y value at x2, which is f of x2, is bigger than the y value of f of x1. You can see that the y value here is higher than the y value here. And that's true if I pick any pair of points. It doesn't just have to be at the ends. That's what it means for a function to be increasing on the interval. If this is confusing to you, if you don't like x1 is less than x2, you could just as easily write x2 is greater than x1. They mean the same thing. If x1 is less than x2, then x2 is greater than x1. So I don't know which one of these two things you find more intuitive. Maybe I'll write x2 is greater than x1. x2 is on the right and x1 is on the left. If you like x1 less than x2, which means exactly the same thing, that's totally fine. And let's do another part of this. A function f is said to be decreasing on an interval I if for all pairs of x values, x1 and x2 in I, where, again, I could write x1 is less than x2 or x2 is greater than x1. I'll write x2 is greater than x1. Then the y value at x2, the point on the right, is less than the y value at x1. Now notice I left this the same. x1, x2 is greater than x1, x2 is greater than x1. Both, it was like that in both cases. I could have written x1 is less than x2. It would have meant the same thing. But the only thing I changed was which of these 2 points. I changed the sign right here. If you change them both, if I were to change that sign and change that sign, we'd still have this definition. We'd still have the point on the right is bigger than the point on the left. Saying the point on the right is bigger than the point on the left is saying that the point on the left is lower than the point on the right. They mean exactly the same thing. So I have to switch just one to get the reverse definition. And again, if I have a picture, if my interval I goes from here to here, then for any points in I, x1, x2, the point on the right is lower than the point on the left. So here's f of x1, and here's f of x2. It has to be true for any pair of points, not just the endpoints of the interval. Not just the endpoints of the interval. Because it's possible to have a function, let's say I have a function that looks like this. Here's my interval, whoops. Here's my interval. Let's say the interval goes from here to here. There's my interval, and let's say the interval starts here, and it goes up for a while, and then it comes down here. Well, the point on the right is certainly higher than the point on the left, but you couldn't say that this function is increasing on this interval. It increases for a while and then it decreases. It has to be for any pair of points. For increasing, the point on the right has to be the higher of the two, and for decreasing, the point on the right has to be the lower of the two. Okay, if that's understood, I want to talk about a theorem. I suppose before I go on to that theorem, and I see I've erased half of it already, but at least we have the definition of decreasing still there. Notice that the definition of increasing, which is still in your notes, and the definition of decreasing don't mention the word derivative at all. If I ask you, say on a test, for the definition of increasing, I don't want to see the word derivative as part of your definition. Instead, I want you to talk about pairs of points and the point on the right being higher or lower, depending on whether we're talking about increasing or decreasing. It does not mention the word derivative. That being said, we have an important theorem. If f is continuous on the closed interval AB, and secondly, f is differentiable. This should ring a bell. This should look exactly like what we had for for Rolle's theorem and the mean value theorem. F is differentiable on the open interval AB, then if there's three things. If f prime of x is positive for all x in the interval AB, then f is increasing on AB. That doesn't mean derivative is part of the definition of increasing, but if it so happens that the function is differentiable and continuous, then this implies that it's increasing on that interval. If f prime of x is less than 0 for all x in AB, then f is decreasing on that interval. Oops. We can actually do a little bit better than this. We can put these in square parentheses, in square brackets. And lastly, if f prime of x equals 0 for all x in AB, then f is constant. It's a horizontal line on that closed interval. So it doesn't mean that increasing, the definition of increasing is that the derivative is positive. You can have increasing functions which have no derivative at all somewhere. If I have a function like this, you can see that that function has a sharp turn right there. It has no derivative there because we know derivative means smooth. But this function is still increasing on from there to there because if I pick any 2 points, the point on the right is the higher of the two. I can even have a discontinuous curve which is increasing. If I pick any 2 points in the interval, the point on the right is going to be the higher of the two. So the definition of increasing does not reference the word derivative at all. However, if it so happens that the function is nice and smooth, then if the derivative is positive everywhere, the function is increasing. If the derivative is negative everywhere, the function is decreasing. And if the derivative is 0 everywhere, it looks like a horizontal line.